Welcome to Nigeria Society of Engineers, Manchester branch technical session titled A Step Towards Digital Engineering in the Metaverse. And this is in continuation of our theme for Q2, which is digital inclusion and transformation. Today's guest speaker is Professor Lee Margetts. Our technical secretary, Dr. Akilu, will read the guest speaker's bio shortly before his presentation. My name is Engineer Patrick Obidoyin. I'm the Publicity Secretary of Nigeria Society of Engineers, Manchester branch. We welcome you all. I wouldn't want to take so much time. It might interest the guest speaker to know that there was over 70 registrants for this particular technical session as of yesterday. So we expect more, hopefully, at this time. I would give the floor now to Dr. Obuks Ejohumo, the branch chairman, for his opening speech. The chairman, you have the floor, sir.
Thank you very much, Engineer Patrick Obidoyin, and a very warm welcome to all our delegates here today. It's always a delight to warmly welcome you all. Like Patrick has said, my name is Obuks Ejohumo. I'm the chairman of NSC Manchester branch. By way of opening remark, I just want to let delegates know that as a branch, we are continuing to wax very strong. We have over 200 active members in the branch as of today and still counting. As part of our focus for 2022, looking at membership welfare, we will be having our summer event on the 30th of July, come 30th of July. That will be an opportunity for us to have our first in-person interaction, and we wanted to make it very, very relaxed. So we'll be meeting on the 30th of July. So if you haven't registered, please use the opportunity. We'll circulate the participation form for that event. Please register, and all are welcome to attend for that event. So without much ado, I think I will invite Akilu to please welcome our special guest speaker today in the person of Professor Lee Margetts. Thank you.
Good evening all, and welcome to today's technical session. So now before I introduce the speaker, he's made me aware that he's got another commitment about this time somewhere else, which might be in a very noisy environment. So what we've done in order to counter that is he's pre-recorded this session. So he's actually at a football session for his son. So we've pre-recorded the session. I'll play the pre-recording, but he's online actually through a mobile device. So questions would be answered in real time. So no experience, the experience will be comparable, and so I'm just making people aware. Okay, so Professor Lee Margetts holds a BSc honors in geology from Durham University, then studied for an MSc in geotechnical engineering, an MBA in international engineering business, and a PhD in civil engineering, all from the University of Manchester. Lee is currently the chair of the UK Atomic Energy Agency, UKAEA, for fusion energy. He's also the program director for mechanical engineering undergraduate program at the University of Manchester, as well as the chair of the International Association for Engineering Modeling, Analysis and Simulation Community, which is a non-profit organization that focuses on the practical application of numerical engineering simulation techniques, such as the finite element method for structural analysis, computational fluid dynamics, and multi-body simulation. He's also been the chair of the Partnership for Advanced Computing in Europe Industrial Advisory Committee. He was a reader in structural integrity. He's once the head of modeling and simulation teaching group at the University of Manchester, once the lecturer and senior lecturer in high performance computing and a consultant. He's been a visiting research fellow at the University of Oxford and the civil engineer at Surrey County Council. So this is just an abridged extract of his bio. So he'll be our speaker for today. And so I'll just share his video in a moment. So thank you very much, Lee. I know this was really the notice was short, but he was still able to pull it off. So just give me a second. Can you see my screen? Can you see a video?
Yeah, we can see it.
Okay, so let's see. You can still see the video. A step towards.
Yes, we can.
Okay. Please let me know if the volume is fine as well.
No volume yet, sir.
Sorry, did you say no volume?
Yes.
No volume yet.
Yes, sir. No volume, sir.
Sorry, that's quite strange. Because I could.
Now we could hear you, but upon playing the video, no volume.
That's a tricky one because let me see, share system volume. So just a second, I'll just try something else. Did you hear that?
Not yet.
Please just bear with Akilu. I'm sure we'll get it working in a bit.
So just give me a second. I'll just try logging on and I'll try sharing it on another device. Maybe because I could. Just a second.
Recording in progress.
A second.
My name is Lee, and I'm going to be giving a presentation titled A Step Towards Digital.
We can hear now.
Can you hear him? Okay.
Yes, we can hear you now.
Okay.
Yeah,
So
we can hear you now.
I'll just take you back to the beginning, if that's okay.
Two new research groups, tritium fuel and digital engineering. And this project that I'm going to present today is one of the first. My name is Lee, and I'm going to be giving a presentation titled A Step Towards Digital Engineering in the Metaverse. This work has been supported by many colleagues from the University of Manchester, from Imperial College London, the UK Atomic Energy Authority, and NVIDIA. Recently, the University of Manchester and the UK Atomic Energy Authority signed a new research partnership to create two new research groups in tritium fuel and digital engineering. And this project that I'm going to present today is one of the first outputs of that new agreement. So, what are we going to look at in this presentation? I'm going to give a quick overview of the metaverse. We're going to have a look at how nuclear fusion works, and then we're going to see, we're going to take a look at the International Fusion Roadmap and talk a little bit about the challenges faced by engineers and why the use of the metaverse to support engineering might help bring fusion energy to the electric grid much earlier than anticipated. And we're going to have a look at a key technology called the Omniverse, which is a platform for developing the metaverse. And we have evaluated this as a potential software stack or platform for developing a new capability for engineering. And then I'll summarize our findings. And really, this is a call to arms for all engineers in this area, and in fact in other areas, to consider the adoption of new technologies for engineering. So, what is the metaverse? So, if we go back to 1989, we had the invention of the World Wide Web. And very early on, or very soon afterwards, we had already had people thinking about what the three-dimensional virtual space or virtual equivalent of the World Wide Web might look like. So if we think about the World Wide Web or the internet as two-dimensional, then basically the metaverse is the 3D equivalent. And this brings in technologies like augmented reality and virtual reality. And the idea is, to create links between the physical and digital worlds. And we get, you know, we get the idea that we're moving, you know, that the metaverse may be the platform for digital twins. So whilst Mark Zuckerberg is looking at this technology from the point of view of social media, what we're doing in this presentation is considering this as a future tool for carrying out engineering. So a long time ago in my career, I was fascinated by the apparent convergence of various digital industries. So film production, engineering, and gaming. So on this picture on the left here, we can see a workflow of film production. So we have the pre-production step, production, and post-production. Now, if you have got knowledge of engineering and engineering simulation, we have a very similar workflow. We have pre-processing, which is the creation of the model, or the idealization of reality into a computer model. Then we set up a system or a physical problem that we solve using different numerical techniques. And then we have a post-processing stage whereby we gain, we seek to gain some insight into, the engineering problem from the results of the simulation. So there are very strong overlaps between these three areas. And in fact, they share three business drivers. The need for increased realism. So computer games are getting, more and more, they look more and more realistic. Obviously in the film industry and special effects, there's a desire to make them look like real life. Each of these industries involve very large interdisciplinary teams that are often geographically dispersed. So we need, each of these areas need technologies to support large teams. And also each sector has pressure to deliver a product in a short period of time. So the computer games, maybe the pressure is to deliver a new game before Christmas, and a film, in time for, particular slots available in cinemas or on Netflix. And so there's these three common drivers. And each of them can be supported by this software that is developed by NVIDIA called the Omniverse. Now, the Omniverse provides realism through very highly optimized visualization tools, and it also incorporates physics engines that are enhanced by artificial intelligence or machine learning algorithms. In order to support large teams, the Omniverse has a client-server architecture, and the server looks after assets, for example, CAD geometries, or the geometries of assets that are used in a computer game or in a special effects in a movie or in an animation. And the Nucleus server also has microservices for managing the permissions of each individual that works in a team. So giving them, allowing a manager to configure permissions as to what aspects of the workflow that we saw in the previous slide, a particular individual in a particular team can modify or change. And then from the point of view of time, one of the biggest barriers, or one of the things that is very time consuming, is collaboration. And so NVIDIA have thought about this from the point of view of having a common data format in their platform. So they've adopted Pixar's universal scene description format. And what they're pitching in terms of that format is that this would be the equivalent of HTML in the internet. This would be the preferred platform or the preferred format for the metaverse. And various software vendors have their own preferred formats, and so there is technology called connectors, which allows third-party software to be integrated into the Omniverse, where the data exchange is passed through this universal scene description format. And one of the, lots of big engineering companies are interested in this technology, not just the fusion community. And so, the example that we see here is a virtual factory, that's been created by BMW, and they've basically used the metaverse or the Omniverse to improve their production line. And there's videos on the internet that that would be, if you're interested in this, that I recommend that you use Google or a preferred search engine to follow this up. So let's go back to fusion. How does fusion work? Basically, we have to heat hydrogen to very high temperatures. This causes the atoms to fuse. Helium is given off as a waste product. Neutrons are released, and the neutrons heat water, and then we're into a process that is exactly the same as any other power station. So a gas, oil, or coal-fired power station. The water is heated, turns steam, drives turbines, and generates electricity. Now, we're very confident that we understand the physics of this process, and so now the challenge is to create or build a power station, and this moves us on to engineering. So what does the roadmap look like? So if you look at this orange line, JET is a European facility built originally in the 1990s and still operating now. And this was built as an experimental facility to understand the physics. ITER is currently being built in France in order to, for us to be able to get more understanding of, what is needed to build a power plant. Demo is in the future beyond ITER, and the idea is that, this would be a plant that would start generating electricity, and eventually we'd have the experience and knowledge in order to build a power plant to generate electricity. Now, the UK government have got more ambitious plans, and so we have the STEP program, which is a spherical tokamak for energy production, and the UK government is funding a program that aims to deliver a prototype energy plant by 2040. This is extremely challenging, and if we have a look at the engineering, basically, if you look at this purple color, this is a plasma. This is where the fusion process is taking place. It is hundreds of millions of degrees in temperature, the hottest known place in the universe, and there are no materials that can withstand these extreme heats. So we have to use magnets, magnetic fields, to keep the plasma away from the walls of the power plant. And the power plant is a very complicated machine with hundreds of thousands of components. So as well as having to deal with the plasma, we have all of the usual engineering challenges. So if we think about just the general structural engineering, will the structure support its own weight? There's additional complications because where the plasma is, it's a vacuum. And then we've got these very strong magnetic fields. So there's, the structural engineering problem is quite complicated. Then we've got these neutrons. So the neutrons are passing through all of the materials of the power plant, and neutrons will or may weaken materials that have been selected to build the power station. And this loops back into, the structural design. Will the design of the structure support the loads when the materials are weakened? And if that's not complicated enough, we've got lots of different subsystems. So an example here is a cooling subsystem. So what we've got is a complex interplay between different components and different areas of physics and engineering. So we've got stress, we've got heat, we've got magnetic fields, we've got particles passing through the materials. And if we take the approach of allowing a structural engineer to work in isolation, if there's a change in any of the other systems, this will have a knock-on effect on that work. So we need to consider the design of the power plant in a holistic way. We can't, we can't just work on individual components in isolation. If we could, live in a world that's a bit more like science fiction, or in 100 years' time, maybe we would have software that would allow us to simulate the whole machine, interactively and play about with what if scenarios. But we don't have that at the moment. We've got our current engineering design tools. And it is the opinion in the fusion community that if we took the largest supercomputers in the world, we took advantage of artificial intelligence and machine learning and platforms or technologies like the Metaverse, maybe we would be able to build a design platform for fusion energy or other challenging engineering areas that that could bring forward fusion energy as a power source for our electricity grid. So before I was appointed chair, in fact, before I was interviewed for the chair position, I put in a proposal suggesting that we evaluate the NVIDIA Omniverse for digital engineering. So this presentation basically presents the results of that evaluation. And we're currently working on a proposal, for phase 2 of the project to develop a proof of concept platform for digital twins using this technology. So our evaluation centered on 4 questions. One thing we wanted to know was whether it was difficult to add extensions to the Omniverse for scientific software. Another aspect was that NVIDIA has got a very powerful and compelling and persuasive marketing team that try and persuade us to buy their products. So one of the aspects of the marketing is that the platform supports collaboration between design teams. So we wanted to have some funding to have a look at that capability and to see, whether the marketing was to be believed. So this is another aspect. And the final 2 involve the capability of photorealistic rendering. So this is the realism that I talked about earlier. Could this benefit robotics, and could it benefit some aspects of operation of the power plant? So let's have a look at the first one. So basically what we did was a learning by doing exercise, and we did integrate a scientific software which is used for tracking the path of subatomic particles through matter. So this is called GANT4. And these green lines you can see in this picture are the particle paths. And so in order to implement this software, scientific software, into the Omniverse, first we had to have a way of launching or allowing the user to launch a job. So basically, the Omniverse allows developers to create a graphical user interface. So basically, to start with, as a proof of concept, we created a button which launches a job. Then we needed to take all of the different packages and scripts used in the scientific workflow to carry out this particle path simulation, and we packaged them using containers, and we also packaged them in a workflow tool, or what they call a workflow orchestrator. So this basically has all the software, and then we have to remember that the user may want to configure the software to set values of certain parameters, to provide the CAD, the computer-aided design geometry of the machine through which the particle paths want to be traced. So we've got these three elements, and then once those are, those have been developed. So from the user point of view, they press a button in the Omniverse. This launches the workflow that carries out the science, and this can run on the same workstation as the Omniverse, or completely separately, on the cloud or on a supercomputer. When finished, the results are returned to the Omniverse, where they are visualized. Now, the development to enable this was very straightforward, and the only thing that took time was writing scripts to convert from the native universal scene description format to the format required by the GN4 engineering software. So the next thing that we looked at was support for collaboration. So in many engineering fields, we've got distributed teams of engineers working using their own favorite packages that their companies have paid the licenses for. And so collaboration may be slow because they'll be working on different aspects of the design, maybe having to share files via email, and the information may be in different formats and different packages. So this is a bit of a headache for a manager. So how does the Omniverse deal with this? How does it improve collaboration? So I've got a video here that's been produced by my colleague Omar, and I'm going to play that now.
In this video, we will talk about design and visualization of the component of a fusion reactor in Omniverse to improve and accelerate the design process. We will be looking at some of the distinct features of Omniverse which sets it apart from any other design package. These features include multi-user collaboration, one-way and two-way connectors, real-time interaction, photorealistic rendering, and version control. Now let's look at a quick demo. Here we can see three different engineers working on three different components of a reactor in three different packages from three different locations connected via the nucleus using one-way and two-way connectors. Any changes in any of the packages gets updated in real time in the Omniverse without the conventional file sharing and import and export process. We can add or remove components, or we can even edit the existing components. We can also create new components within the Omniverse using the creation tool, and the changes are updated throughout the pipeline. We can add lightning effects for photorealistic rendering using the RTX path traced feature and see how the light behaves from different angles and distances. We can toggle different views and observe the changes clearly. The nucleus also supports historical versions of files called checkpoints. The design engineers can add checkpoints with a description in each design stage to revert back to any changes as part of the design iteration process, or even discuss and compare different design options in the workspace view. Here we create two different versions of a component of a reactor. We will apply new textures such as carbon steel from the Omniverse material library and observe how the light behavior changes. And then we compare this with the previous version, which includes textures from the native app. On the left is the latest version, and on the right is the previous version.
So we'll move on to the next item. This is robotics. So inside a fusion reactor is not a very nice place for a human being. So we'll be using robots in order to do maintenance. And one of the things that, one area that researchers are looking at now is the use of digital twins to plan tasks, for setting up the robots. With the NVIDIA technology, so we can see here on the right, we have a typical visualization of in a virtual space. Now, with the NVIDIA technology, the rendering is photorealistic, and in many cases, some of the things that they do, and if we look at, if you go back to the BMW factory, what they're trying to do is to create an environment where the scene looks much more like the physical twin, which is on the left of this screen. So if we can have a synthetic environment or a virtual space where it looks like real life, maybe we can use that virtual space for training robots in an environment that looks very similar, with cameras and sensors and things like this, so maybe a game changer in terms of robotics. Keeping on that theme, so this is the Mast the Mast upgrade reactor that we saw earlier in the talk. It's got viewing ports whereby we can have a look at the plasma. So on the top left hand of this image, this is a still from a video feed of a real plasma in that facility. What the operator wants to know is, wants to know some diagnostic information about the plasma based on this picture. And what what engineers are doing at the UK Atomic Energy Authority is they are simulating synthetic plasma and then using machine learning to solve the inverse problem as to what is the composition of the plasma, or things like the temperature. So on the bottom of this diagram, you can see orange and purple pictures. On the far right hand corner, there's the temperature of the plasma, and these are all generated from a synthetic simulation of the plasma using neural networks. So what we want to be able to do, and what we can do, or we believe we can do with the Omniverse, is through the photorealistic rendering, we could put a simulation of the plasma. So this is actually, you'll see here, a simulation of the plasma inside a digital copy of the reactor, and the light coming off the plasma will be reflected off the walls of the reactor, and we should be able to get to a situation where we could look through a virtual viewing port in the reactor and take virtual photographs or virtual videos of what can be seen through the viewing port and use that to train a control system using artificial intelligence for the reactor. Now, this particular video animation has been created by somebody working in the movie industry, and that's why they've chosen materials like glass walls for the reactor instead of the real materials. So what's our conclusion? The conclusion is that technology being developed to create the metaverse could be used to create or to build the digital engineering platforms of the future. We believe that this technology is going to help us, if it's adopted and developed in the engineering sector, will help us deliver fusion energy to the power grid in the shorter possible time. And if you're interested in reading about this work, there's a very nice article in the online magazine, HPC Wire. So that's the end of my talk. So thank you very much for your attention.
Thank you very much, Professor Lee Margetts, for that interesting insight. I hope, Akil, can you double check whether Lee is here to pick questions?
Yeah, Lee should be here. I saw him earlier on, so I'll just check again.
Yep,
Lee.
I'm here. Can you hear me?
Yes, Lee, we can hear you. You sound far, just like your recording did.
Yeah, okay. Yeah.
So thanks once again. We'll ask colleagues. I know you said you're on the football pitch, so it might be better. Yep. Would you prefer that questions are typed in the chat box?
No, it's okay. It's okay. I can hear fine.
Okay. So, Chairman. Yeah.
Thanks, Akilo. So thanks, Lee. I hope your son's team is winning. To start on a lighter note, I can see Grenfell has got his hands up. Let me go straight to Grenfell before I ask mine. Grenfell, please.
Good evening, Chair. Thank you so much for the opportunity. And I want to say a very big thank you to Lee for this informative and insightful presentation. I carefully listened, and one key aspect I got was the fact that this key aspect of digital technology is being applied in the manufacturing sector and also in power, energy production. And you made one key